This video is part 2 of your Unit 2.9 Gas Chemistry, and we're going to be starting with looking at oxygen on page 9 of your booklet. So looking at oxygen, again we're going to look through its properties, the test for oxygen, how we prepare it, some of its uses and some of its reactions. So oxygen is the most abundant element in the Earth's crust, but as we know it's not the most abundant element in the Earth's atmosphere. Which element is that? That's nitrogen. Oxygen makes up, you should be familiar with this and have learnt this, oxygen makes up 21% of the atmosphere. You can write yourself a little reminder of that if you wish. Again, oxygen has the formula O2, just like with hydrogen was H2, nitrogen was N2, and that's again because it's diatomic, meaning that each molecule of oxygen consists of 2 oxygen atoms covalently bonded together. Let's have a think about what each oxygen looks like. So oxygen is in group 6, which means it has 6 electrons in its outer shell. You can see in this oxygen atom there are 2 electrons that are on their own. So what oxygen does is it bonds covalently with another oxygen atom. And we see that it's the electrons that are currently unpaired pair up and go in the overlap. So let's draw that on our diatomic molecule here. So the single electrons go in the overlap. And the electrons that were already in pairs become our lone pairs on the outside. And we'll do our 2 lone pairs from the green oxygen atom as well. So that shows the bonding in an oxygen molecule. Again, it's probably unlikely that they're going to ask you to do that in an exam because it's more year 11 content, but they could do. But do know that oxygen is a diatomic molecule, which means it consists of 2 oxygen atoms covalently bonded together. So you can see that there's 2 pairs of electrons in the overlap, which means that oxygen has a double bond in it. The oxygen atoms are held together by a double bond. So 1 pair of electrons is a single covalent bond. We have 2 pairs of electrons in the overlap here. So that's a double covalent bond. Let's have a think about the properties of oxygen. Again, we know that it's a gas in the air, and we know that the air is colourless. It's a colourless gas. So oxygen, that means oxygen, because it makes up 21% of the air, if it was coloured, we would see it, but we don't. It's a colourless, odourless gas. So again, just think of properties of air, and you'll remember those. It's about the same density of air. It's slightly soluble in water, which is important because that's how obviously aquatic life can live. So like fish and even aquatic plants, they need oxygen in the water to be able to do respiration. And so therefore oxygen must be soluble in water. It helps substances burn. So if you think about our test for oxygen, which we looked at earlier in the topic, it relights a glowing splint. That's the test for oxygen. So if a splint is just glowing and you put it into oxygen, it will relight. But we also know that it's our oxygen is part of our fire triangle. So our fire triangle, in order to light a fire, you must have fuel, you must have oxygen, and you must have heat. Remove the oxygen and things cannot burn, so we need oxygen for things to burn. And again, it's a neutral gas, it's not acidic or alkaline. There's your test for oxygen summarised again. So if we want to test a gas to see if it's oxygen, we apply a glowing splint to a sample of the gas. And if it's oxygen, the splint will relight. So again, if you were asked that in an exam, how do you test a gas to see if it's oxygen? Remember, it's first of all, what do you do? So that's this first point, what do you do? Second point is what happens if it is oxygen. So first of all, what do you do? You apply a glowing splint to the sample of the gas. And second, what happens if it is oxygen? That's the splint will relight. Over on the next page we have the preparation of oxygen. And actually we've seen this reaction before in Unit 2.3, which is rates of reaction. But also you might notice from the apparatus that is very, very similar to the apparatus for preparing hydrogen. It's exactly the same. So again, be able to draw this if necessary, or certainly able to label the different pieces of apparatus within it. So again, we've got our reaction happening in our conical flask, and we'll come back to that in a second. And then what will happen is the oxygen gas will travel up the delivery tube into the beehive shelf, and then up into the gas jar, which is filled with water initially, and as oxygen is prepared, it will displace the water and collect in the gas jar. And we can check to see if it's oxygen by applying a glowing splint. If the glowing splint relights, then we can tell it is oxygen. So again, it is collected over water, so that key phrase of being collected over water is really important, so you can highlight that, and that will be going on your mind map summary sheet as well. So we've met this, as I say, in our rates of reaction topic when we were looking at catalysts. In that topic we looked at the reaction of the decomposition of hydrogen peroxide. So hydrogen peroxide has the formula H2O2. And it decomposes slowly to form water and oxygen. To balance that equation, we need a 2 in front of our hydrogen peroxide, and then a 2 in front of our water. So hydrogen peroxide slowly decomposes to give water and oxygen. So if we were to leave a sample of hydrogen peroxide, it would do this eventually. But we can speed it up by adding in a catalyst. It's important that you know the name of the catalyst. Again, we've met this before. The name of the catalyst is manganese, not magnesium. It's a different metal. It's one of our transition metals. Manganese 4 oxide, or also known as manganese dioxide. A couple of ways we can get the formula of that. So we can get it from this name, manganese dioxide. Manganese has the symbol Mn. And dioxide means 2 oxygens, O2. Just like carbon dioxide is CO2, manganese dioxide is MnO2. Dioxide literally means 2 oxygens. If you want to get it from this name, manganese 4 oxide, it's a simple case of doing swap and drop. So manganese, again, the symbol Mn. The 4 in brackets means that the valency of manganese is 4. And then oxygen, look in the periodic table, its valency is 2. I always ask myself at this stage, can I cancel down those valencies at all? Well, yes, I can in this case. I can divide both of them by 2, and that would give me a ratio of 2 to 1. Then when I swap and drop, I'm going to get MnO2. So the formula is MnO2. You can call it manganese dioxide or manganese 4 oxide. Whichever you find more helpful to learn. So again, because oxygen is only sparingly soluble in water, we can collect it over water. So let's have a look again at that equation. So hydrogen peroxide, we said, had the formula H2O2. So you need to learn that formula. It's not one you will see on the periodic table. It's not one you can really work out from the periodic table. So make sure you learn that formula. It decomposes to give water, H2O, and oxygen. To balance it, I can see that I need more oxygens on the left. So I start by putting a 2 in front of hydrogen peroxide. That now means I have 4 oxygens and 4 hydrogens. And I fix that by putting a 2 in front of the water. That now gives me 4 hydrogens and then 2 oxygens within the water and 2 oxygens at the end there as well, which is a total of 4. You will notice that manganese dioxide does not go in the equation, and that's because it's a catalyst. Remember, a catalyst is something that speeds up the rate of reaction but is not used up, so it's not written as a reactant. If you want, you can write it on the arrow, but it's fine just to leave it out completely. And should say there, since manganese 4 oxide is a catalyst, the word oxide is missing there, you could add that in. So since it's a catalyst and it's a solid catalyst, it's not used up, so therefore it can be filtered off at the end, dried out, and then can be reused because it's not actually used up in the reaction. It just provides an alternative pathway for the reaction to happen. So that's how we prepare oxygen. You need to learn that reaction. We prepare it from the decomposition of hydrogen peroxide with the use of manganese dioxide as the catalyst. We're now going to look at the reactions of oxygen, and again these reactions come from the properties of oxygen. We know that oxygen is needed for things to burn, and so therefore when different reactants burn, they will form different products. So there's lots of reactions of simply burning different elements or compounds that will form oxides. What we're going to look at quite a few different examples of burning, the likes of magnesium, copper, carbon, so on. But you also need to be able to classify the oxide products. So say for example you had a metal burning in oxygen, which is the first one here. So a metal will react with oxygen to give a metal oxide. Okay, so metal reacts with oxygen to give a metal oxide. That's your general equation. And metal oxides are always basic. And that's the opposite of acids. So we know a neutralization reaction is where an acid reacts with a base to form salt and water. You might be slightly more familiar with the term alkali. But alkalis have to be soluble, whereas bases can be insoluble. So base is the general term for something that will react with an acid to neutralise it. So an alkali is a specific base that is soluble, but bases is the general term. They can be insoluble or soluble, but they react with acids to give salt and water, in other words, neutralise acids. Non-metals then are the complete opposite. So non-metals burn in oxygen to give non-metal oxide. So if we were to write a general equation, what we mean by that is just non-metal reacts with oxygen to give a non-metal oxide. And non-metal oxides are always acidic. So that's the general rule. So basically you're deciding, is the oxide that I formed in this reaction a metal oxide or a non-metal oxide? If it's a metal oxide, it will be basic, and if it's a non-metal oxide, it will be acidic. So learn that general rule and be able to apply it to any equation, the ones that we're going to look at now, but even an unknown reaction as well. If it's a metal oxide, basic. If it's non-metal oxide, it will be acidic. And we'll come back to that each time we look at one of these individual reactions. We'll classify the oxide product as either acidic or basic. So let's look at the reactions of oxygen. So the first one is combustion, and that's a very general term, but you do need to know the definition of it. It's quite a common question. What is the definition of combustion? So combustion in kind of a junior science sense would just be burning things, but at GCSE you need to be a little bit more technical. So what actually happens when we burn things? Well, combustion is specifically, generalises the thing that you're burning as a fuel. And combustion, then in the form of a definition, is the reaction of a fuel with oxygen that produces at least one oxide and releases energy. So if you think of like burning magnesium, which we'll come on to in a second, if we were to burn magnesium, it would react with oxygen in the air to form magnesium oxide. So if we think, does that fit the definition of combustion? So it's a reaction of a fuel with oxygen. So we're reacting magnesium with oxygen. So yes, it fits that part of the definition. The next part of the definition is, does it produce at least one oxide? Well, the product is magnesium oxide, so yes, it forms an oxide product. And does it release energy? Well, if you think of burning magnesium, it burns with a bright white light. Light is a form of energy, so yes, it releases light energy, and it will also release heat. But we've given a general example here of fuel. Fuel reacts with oxygen to give carbon dioxide and water, but also releases a lot of heat energy. So think of the fuel that you burn at home. Think of even the fuel that we burn in a Bunsen burner, and that is methane. And we'll come on to this when we look at organic chemistry. Methane is CH4. When we burn it, it reacts with oxygen and it produces carbon dioxide and water. To balance that, you can see we need 4 hydrogens on the right, so we need to put a 2 here. Then I've got a total of 4 oxygens on the right, and so I need to put a 2 there. So that's burning methane, which is the gas we use in the Bunsen burners. And that is combustion, because the fuel is methane. We've formed actually 2 oxide products. We've formed carbon dioxide, and we formed water. And water is an oxide product, because what we've done is we've taken the hydrogen, I'll just go over it in green here, from methane, and it's now become hydrogen oxide as such. It's gained an oxygen and become water. So this is a combustion reaction. It reacts with oxygen, produces at least 1 oxide. It actually produces 2 oxides, and it releases energy. We know that when Bunsen burners burn, they form a flame which gives light, so that's light energy and also heat. So combustion won't happen without oxygen because it doesn't fit that first part of the definition, the reaction of a fuel with oxygen. So without oxygen, combustion cannot happen. So combustion is the first general type of reaction of oxygen, essentially burning any fuel to produce at least 1 oxide and release energy. We're going to now look at a few specific reactions of reacting certain elements with oxygen, and essentially that's just burning them, and as long as we form an oxide product and they release energy, then it is technically a combustion reaction as well. So the first specific reaction we're going to look at is the reaction of carbon with oxygen. Now when carbon is completely reacted with oxygen, and that means if there's a plentiful supply of oxygen, there's no limit of how much oxygen there is, carbon will react with oxygen to give carbon dioxide. Try and write the equation, the balance symbol equation for that yourself. So pause the video, try and write it yourself, and then play the video to check that it's correct. So carbon reacting with oxygen, producing carbon dioxide. Carbon is simply C plus oxygen. We know that the formula for oxygen is O2 because it's diatomic. And the formula for carbon dioxide, well, carbon is just C. Dioxide means 2 oxygens. So it's O2, 2 oxygens. And you can see that that equation is balanced. So carbon reacts with oxygen to give CO2. The observations of that reaction is that black carbon burns with an orange sooty flame and produces a colourless gas. That colourless gas is simply your carbon dioxide, or CO2, you could write in there. Now, a slightly different reaction happens if we have a limited supply of oxygen. If there is a limited supply of oxygen, rather than forming carbon dioxide, we form carbon monoxide. So in this case, carbon reacts with oxygen to produce carbon monoxide. Mono means 1. So that means carbon is C, monoxide means 1 oxygen, so it's just CO. Now you can see that that equation is not balanced, so we've got to balance it first. So 2 oxygens on the left and only 1 on the right, so that means I need to put a big 2 in front of my carbon monoxide, and therefore I'm going to have to put a 2 in front of my carbon as well. This is quite a dangerous reaction because carbon monoxide is poisonous, and it is also colourless and odourless. So carbon monoxide is colourless and odourless. It is poisonous because it binds irreversibly to red blood cells. So if you think of red blood cells, their job is to carry oxygen around the body. And if we kind of look on a side-on view of a red blood cell, it has that dip in the middle, doesn't it? For the oxygen molecules. So essentially, the job of red blood cells is to carry oxygen. So oxygen binds to red blood cells, and then it lets go of the oxygen. The red blood cells let go of oxygen when it needs to be delivered to other cells. But what carbon monoxide does when you breathe that in is it binds irreversibly to the red blood cells. And what we mean by that is that it binds to the red blood cells and it doesn't let go. So it bonds almost permanently to red blood cells. And if it bonds permanently to the red blood cells, that means there's no space for oxygen in the red blood cells. And therefore oxygen can't be carried around the body. And therefore people die from suffocation because oxygen cannot travel around their body. So carbon monoxide binds irreversibly to red blood cells, taking up the space of oxygen. So that's obviously very dangerous, and people can die from carbon monoxide poisoning. That's why houses are fitted with carbon monoxide alarms. Because it's colourless and odourless, you can't actually detect it yourself. And that's why you've heard, unfortunately, of people dying from carbon monoxide poisoning because, perhaps they might be asleep. There's a gas leak, there's a leak of carbon monoxide in the house, and that can cause carbon monoxide poisoning. So that's if there's a limited supply of oxygen, we form carbon monoxide instead of carbon dioxide. So just watch out for that in a question. It would simply say, write the equation for carbon reacting with a plentiful supply of oxygen. That will get you carbon dioxide, as we've discussed up here. But if it said in a limited supply of oxygen, it would form carbon monoxide. So it just determines the product formed. And then, as we discussed previously, for each of the oxides formed, we have to classify them as basic or acidic. Remember, the rule was metal oxides are basic and non-metal oxides are acidic. So carbon, we need to think here, carbon is a non-metal. So carbon dioxide and carbon monoxide are non-metal oxides. And so therefore they are acidic. So think the rule, non-metal oxides are acidic. Non-metal oxides are acidic. Carbon is a non-metal, and therefore its oxides are going to be acidic. And that's why the burning of fossil fuels can contribute to acid rain, because the burning of fuels releases carbon dioxide, which when it dissolves in rainwater forms an acidic solution, and that falls then as acid rain. So just to summarise, carbon reacting in a plentiful supply of oxygen gives you carbon dioxide. Carbon reacting with a limited supply of oxygen gives you carbon monoxide. And both of those, carbon dioxide and carbon monoxide, are acidic. I'm now going to play you a video of me burning carbon, just so that you can see these observations for yourself. Okay, so the first reaction we're going to do is the reaction of carbon with oxygen. So we're going to do that by burning some charcoal in a Bunsen burner. So when you burn something, it's reacting with the oxygen in the air. So here's some carbon. You can see that it's a black powder. And let's see what happens when we burn it. So when we burn it, it's reacting with oxygen. So you can see that there's some sparks at the edge. That's because this is powdered charcoal. So some of it's catching on fire. But you can see that it's burning with an orange flame. And hopefully you can also see that it's burning with a slightly sooty flame as well. That can be quite hard to see. But carbon burns with a sooty flame. Think about if you were lighting a fire at home and you were burning some coal. It burns with a sooty flame. And that's essentially what we're doing here. Coal is just carbon. And it burns with an orange sooty flame. So you know that even from lighting a fire at home. Okay, so carbon burns with an orange sooty flame. Now this is assuming that carbon is burning completely, that there's enough oxygen in the air to allow it to burn completely. But if there wasn't enough oxygen in the air, if there was insufficient supply of oxygen, rather than getting carbon dioxide gas, we would get carbon monoxide gas, which is a very harmful, poisonous gas. The next reaction we're going to look at is the reaction of sulphur with oxygen. And similarly to carbon, sulphur reacts with oxygen to give sulfur dioxide. So think about the equation of carbon reacting with oxygen to give carbon dioxide, and see if you can write an equation for the reaction of sulphur with oxygen to give sulfur dioxide. Pause the video, see if you can do that now, and then use the video to check. So sulphur is simply S, oxygen is O2 because it's diatomic, and sulfur dioxide, we get the formula from the name. Sulphur is just S, dioxide means two oxygens, which we write as O2. So it's S plus O2 gives us SO2, and that equation is already balanced. In a minute I'll show you a video of this reaction happening, but in it sulphur is a yellow powder, and when we burn it we're reacting it with oxygen, and it melts initially to form a red liquid. And that red liquid burns with a clean blue flame. That's a key observation to note. It burns with a clean blue flame, and it gives off a colourless gas of sulfur dioxide. But sulfur dioxide is very pungent, and what we mean by that is it kind of chokes the back of our throat. It's a very pungent gas. Let's think of our product, sulfur dioxide. Well, sulfur is a non-metal, so sulfur dioxide is a non-metal oxide. And the rule is that non-metal oxides are acidic. So sulfur dioxide is acidic. So in an exam, if you were asked, is the product of this acidic or basic? Well, you're thinking, okay, it's a non-metal oxide, so therefore it must be acidic. And we've previously talked about acid rain, but actually sulfur dioxide is the key contributor to acid rain. And again, it's released from burning fossil fuels. Fossil fuels tend to have sulfur impurities in them. So if the fossil fuel, if this is a random block of fuel, it'll contain little atoms of sulfur in it as impurities. And then when you burn it, you're reacting it with oxygen. When you burn the fuel, that sulfur will convert to sulfur dioxide and be released as sulfur dioxide. Then that will, that's supposed to be a cloud, it will dissolve in your rainwater and form an acidic solution, because remember, sulfur dioxide is acidic. So the acidic gas dissolves in rainwater to form an acidic solution of sulfurous acid or sulfuric acid, and it falls as acid rain. So I'll show you now the video of sulfur reacting with oxygen. The next reaction we're going to do is the reaction of sulfur with oxygen, again by burning. So when you burn something, it's reacting with oxygen in the air. Hopefully you can see that sulfur is a bright yellow powder, but when we burn it, we're going to see that it's going to change colour, and we'll have a look at the flame that it produces as well. So again, put this on the roaring flame. Okay. So hopefully you can see this, that the sulphur is melting and it forms a red liquid. Hopefully you can see that it's no longer yellow, it's now red, and it's forming a liquid. So the sulphur is melting and forming a red liquid. What I want to do is take it out of the flame, and what you can see that even without the flame, it is, even without the heat, it is burning with a clean blue flame. What we mean by a clean blue flame is one that is not sooty. So clean means not sooty, and you can see the colour of the flame is blue. So it's forming, burning with a clean blue flame, and the gas given off is a very pungent gas. So I'll burn it just a little bit more. Obviously you'll not be able to smell that, but the gas given off is a pungent gas. That means essentially it would like choke the back of your throat, be very smelly gas. And that gas is sulfur dioxide. So when we burn sulfur, it forms sulfur dioxide, and that is a choking, pungent gas. So sulfur is a yellow powder that when reacted with oxygen, it melts to form a red liquid. It burns with a clean blue flame and forms a pungent gas. The next reaction we're going to look at is the reaction of magnesium with oxygen, a reaction that you should be very familiar with. We did this in our reactivity series topic, and you have done this plenty of times in junior school as well. So again, I'd like you to try and write the equation for this reaction, the balance symbol equation. So magnesium reacts with oxygen to give us magnesium oxide. This time you will need to use swap and drop to get the formula of your oxide product, magnesium oxide. So you'll need to use the valency of magnesium and the valency of oxygen, remembering that it's not diatomic when it's part of a compound. So pause the video, try to write the balance symbol equation yourself first of all, and then you can check it with the video. So to write the balance symbol of the equation of this, you just convert each term to its formula. So magnesium is Mg plus, and then oxygen is diatomic, so it's O2, and that's because it's in its element form. Oxygen as an element is diatomic, but when it's part of a compound, it's not diatomic anymore. So magnesium oxide, as I said, we have to do our swap and drop for that. So magnesium, first of all, is Mg. Look in your periodic table, you'll need that out in front of you. If you don't have it already, please pause the video and get that out. Magnesium is in group 2, so it has a valency of 2. Oxide is just simply an oxygen atom that has become an oxide ion when it's reacted with magnesium. Oxygen is in group 6, and so it also has a valency of 2. We don't include the little 2 at the end. It's not diatomic anymore now that it's part of a compound. I asked myself, can I cancel down those valencies? Yes, I can. Divide both of them by 2 and you're left with a ratio of 1 to 1. When we swap and drop that, we ignore the 1, so it's just MgO. If you've got to this stage and you think you could balance it, then please pause the video and try and balance it. And just to check that, you can see that we've two oxygens on the left but only 1 on the right. So we need to put a 2 in front of our MgO. That gives us 2 magnesiums as well, so we must put a 2 in front of the Mg on the left. So that's your balance symbol equation. 2Mg plus O2 gives us 2MgO. So again, you should be very familiar with this reaction. I'll show you a video of it in just a second. But we know that the shiny grey solid of magnesium burns with a bright white light. So think of your 3 words that rhyme. Bright white light. It releases heat and it produces a white ash of magnesium oxide. Again, you have to decide whether the product is a basic oxide or an acidic oxide. Again, remember your rule. Non-metal oxides are acidic, and metal oxides, this is the first example that we've met, metal oxides are basic. Magnesium is obviously a metal, so it forms a metal oxide of magnesium oxide, and therefore it is basic. So again, you don't need to learn each one of these in turn, just learn your rule. Non-metal oxides are acidic, metal oxides, as with this case, are basic. The next reaction we're going to do is the reaction of magnesium with oxygen, again by burning it. So you can see that magnesium is a shiny grey metal, and when we burn it, this is a reaction you've seen right from first year, it burns with a bright white light. So think of the 3 words that rhyme, a bright white light. And what we're left with, I'll just burn this last wee bit at the end. Okay, so you can see that bright white light again at the end. Okay, and once it has completely burned, it forms a white ash or a white powder. Hopefully you can see that on the heat-proof mat there. So you refer to it as a white ash or white powder. So magnesium burning, reacting with oxygen, it burns with a bright white light and forms a white ash. The next reaction we need to look at is the reaction of iron with oxygen, and actually the balance symbol equation is written for you here because it's a little bit different and it's a little bit complicated. We can't quite get our formula for the iron oxide from swap and drop, so I've given this to you here. So you can see iron is reacting with oxygen to give iron oxide, as we would expect. This formula here of iron oxide you need to really learn, because as I say, you can't get it from swap and drop as such. They might specify that it's iron 3 oxide or iron 2 oxide, in which case you could, but if they just write iron oxide, you need to learn this formula Fe3O4. Where does that come from? Well, it comes from the fact that in reality you form some iron 2 oxide, which would have the formula, well, that's iron with a valency of 2. Oxide is just oxygen with a valency of 2. Those cancel out, and so you would just have FeO. But you'll also form some iron 3 oxide. So that's iron with a valency of 3, oxygen with a valency of 2, and when you swap and drop that, you get Fe2O3. So you get some of each of these, and they kind of combine. So literally just combining those two formulas together, you've got 1 iron here and 2 here. That's a total of 3. And then you have 1 oxygen here and 3 oxygens here, and that's a total of 4 oxygens. So that's where your formula of Fe3O4 comes from. That's not a full explanation as such, but gives you some idea where that comes from. And so that's where we get our balance symbol equation from. So really look at that in particular and learn that one, because that is a little bit more complicated. Again, our observations we'll see in a video in a second. When we looked in our reactivity series topic, when we burnt an iron nail, it just changes to black. It doesn't really burn as such, but if you have iron filings, so little powdered granules of iron, they will burn with orange sparks, but they'll form a black solid of iron oxide. And then again, deciding whether it's acidic or basic, it just goes back to our rule. Iron obviously is a metal, so iron oxide is a metal oxide, and therefore it is basic. The next reaction we're going to do is the reaction of iron with oxygen, and we're going to be using iron filings, which is essentially iron in some fine granules. So again, I'm going to heat them in my Bunsen burner. And what you should see with the iron filings is that the iron filings themselves burn with orange sparks. Hopefully you can see those small orange sparks there. However, if I was to burn an iron nail, it wouldn't appear to do very much. We know that iron is quite low down in our reactivity series, and when we burn an iron nail, it simply turns black, so it doesn't actually burn as such. But this iron in its powdered form, in its small granule form, will burn with these orange sparks. But you'll see what we're left with at the end is just a black solid. So essentially iron just turns black, but these filings will burn with orange sparks if they're nice and fine powder. So iron filings burn with orange sparks, and the metal changes from a grey colour to black, and we're forming iron oxide. Our final reaction of oxygen is with copper. So we're going to look at how copper reacts with oxygen. Again, one that we've done in our reactivity series topic. And if you think about it, copper is at the very bottom of your reactivity series. Generally, it just essentially changes to black. But you'll see in the little video that it'll burn around the edges. It'll burn with a blue-green flame. But we'll see that when we come on to the video. So I'd like you to pause the video and try and write your balance symbol equation for this reaction. Copper plus oxygen giving you copper 2 oxide. That little 2 in brackets just shows you that the valency of copper is 2. So give that a go now and see if you can write the equation for that. Pause the video and then watch it to check your answer. So having a look at this equation, what we see is we've got copper, which is just Cu, plus oxygen, which is O2, giving us copper 2 oxide. That means copper has a valency of 2, as does oxygen. So those cancel out to give you 1 to 1, or you can just think of them cancelling out completely and giving you CuO. That equation is not balanced. You can see you've got 2 oxygens on the left So I need to put a big 2 in front of my copper oxide. Now I've got 2 coppers as well on the right, and so I need to put a 2 in front of my copper. So you need to be able to write the equation for that reaction. We're going to see our observations in a minute of this reaction, but again, you have to decide whether your metal oxide formed is acidic or basic, so your oxide product. Obviously copper is a metal, so therefore the oxide, copper oxide, is a metal oxide, and our rule says that metal oxides are always basic. The next reaction we're going to do is the reaction of copper with oxygen. Again, we're going to do that by burning copper. So if you can see here, copper is a red-brown solid, or sometimes referred to as a pink-brown solid. And let's see what happens when we burn it in a Bunsen burner. So what I want you to be looking out for is a blue-green flame. Sometimes we only see glimpses of it, but there we go, and there's the nice green flame there. So copper burns with a blue-green flame, just around the edges, because in the metal we have copper ions, and it's copper ions. If you think back to your flame test from last year, copper ions within a salt, you can see there a wee bit more of the green flame. Copper ions within a salt will burn with a blue-green flame. That was your flame test from last year, which again you need to know for your practical exam. So we can see that it burns with a blue-green flame initially. You can see a little bit more there. And what we then form is a black solid. So on the surface of this copper, we form a black solid of copper oxide. So if you remember back to the reactivity series, copper is right at the bottom of the reactivity series that you learn. And so when we react it with oxygen, essentially it's just changing colour. Essentially it's just changing to black, forming this layer of copper oxide on the surface. But the copper that does burn, we can see that it burns with a blue-green flame. So if I take that out of the Bunsen burner and allow it to cool down, you can see that now it's completely black. And that layer on the outside is copper oxide. So copper reacts with oxygen to form copper oxide, which is black. So that's all the reactions of oxygen that you need to look at. So just to remind you what you need to learn for each one. So for each reaction of oxygen that we've gone through, you need to learn the observations. So you need to be confident what actually happens, what do we observe when that reaction is taking place. You need to be able to write a balance symbol equation for each reaction. Remember, one to watch out for is that iron one, where iron oxide is Fe3O4. And then you need to state whether the product is acidic or basic. And remember, the rule is simply, if it is a metal oxide, then it is basic. If it is a non-metal oxide, such as sulfur dioxide or carbon dioxide, then it is acidic. So it's a simple rule. Metal oxides are basic, non-metal oxides are acidic. The last part of this section of the topic on oxygen that we have to look at is finally the uses of oxygen. So we've looked at its properties, how we prepare it, its reactions, and now we need to look at its uses. So the uses of oxygen, first of all, that it's used in breathing apparatus to help people who have breathing difficulties or breathing conditions, or maybe are in hospital recovering after surgery and so on, and maybe have low oxygen levels in their blood. Then oxygen is used in breathing apparatus to give them a higher supply of oxygen so they can do respiration and survive. It's also used to make steel, and it's also used in the welding process to try and get those really high temperatures in order to join two parts together, whatever that material may be. So in order to make the flame that you're using to heat with nice and hot, you're using oxygen, in some cases a higher percentage of oxygen than would be in the air. So your uses of oxygen are simply in breathing apparatus, to make steel, and in the welding process as well. So what I want you to do now is take a bit of time and complete your oxygen mind map for this topic. If you don't have one, you'll need to print one out, or you'll need to draw it out from scratch. So I'll show you that on the next page. So here's your mind map for oxygen to summarise it. You can see that it's a little bit busier than the other ones we've done so far. So you've got your physical properties first of all. So what are your 5 properties of oxygen? What is your test for oxygen? So the test is what do you do? And the positive result is what happens if it is oxygen. So in other words, your test is apply a glowing splint. Your positive result is the splint will relight. Your preparation then as well, go back to your notes for that. What is the reactant? What is the chemical that we use to prepare oxygen? What is and I would write the balance symbol equation for this one. How do you collect it? How do you collect the oxygen? And what is the catalyst we used in this process? You've got your uses of oxygen, which we've just discussed there. In here, in your central part, I would probably put O2. And if you can fit in your little bonding diagram for that, you can do that. And then down below we have your reactions, which will probably take you the longest time. You'll probably struggle fitting in your observations in some cases, but do your best. So for each, you're writing your equation. I would write your balance symbol equation, even for sake of space. Observations, what do you see happening in that reaction? And is your oxide that you form acidic or basic? And just go back to your general rule. Non-metal oxides are acidic, metal oxides are basic. And you can see with carbon here, you've got A and B. First of all, in excess oxygen, and then in a limited supply of oxygen, have a think about what difference does it make if you burn carbon in excess oxygen or in a limited supply of oxygen. So take some time now, pause the video, complete that mind map before moving on to our last gas, which is carbon dioxide. So our final gas is carbon dioxide, and again we're going to look at its properties. How do we test the gas to see if it's carbon dioxide? How do we prepare carbon dioxide? What are some of its reactions and some of its uses as well? So properties, first of all, again, it's a colourless, odourless gas. Think about it, there's carbon dioxide in the atmosphere, we can't see it, we can't smell it, so it's colourless and odourless. It is denser than air, so carbon dioxide is more dense than air, so it will kind of, if you had, for example, a test tube of oxygen or so on, it would be kind of at the bottom of it. It would sort of sink to the bottom of that container, so it's more dense than air. It's slightly soluble in water, which we'll see, what we'll come back to in one of its reactions. It doesn't burn, so we can't set it alight as such, but also substances will not burn in it. So you know that if you're blowing a candle out, that you're blowing carbon dioxide over it, and substances will not burn in it, so the flame will go out. So if you were to put a lit splint in a container of carbon dioxide, the splint would go out. That's not the test for carbon dioxide as such, we'll come back to that in a second, but things cannot burn in it. And we know that it's an acidic gas, and we know that because we've just studied that carbon dioxide is a non-metal oxide, and we know that non-metal oxides, the general rule is that they are acidic. So again, carbon dioxide levels in the atmosphere, they can lead to acid rain because it's an acidic gas, so if it dissolves into rainwater, it will make the rain acidic. Then your test for carbon dioxide, this is one you should be familiar with as well. The test for carbon dioxide is to bubble the gas through lime water, and the lime water will turn from colourless to milky if the gas is carbon dioxide. So again, the first point is what do you do? And second point is what happens if the gas is carbon dioxide. So up to now, your test for hydrogen and oxygen involved applying a splint, either a lit splint or a glowing splint. This is a little bit different. So if you were testing a gas to see if it was carbon dioxide, you would need a boiling tube or some sort of container that contained lime water. Lime water is a solution of calcium hydroxide solution, and we'll come back to that in a second when we look at the equation for it. But if we were to test a gas to see if it was lime water, we would need a delivery tube and bubble the gas or the carbon dioxide through that delivery tube into your lime water, and the lime water would turn from a clear colourless solution to milky. So you have to say that it turns from colourless to milky. They also accept cloudy, but milky is preferred. And as it says, we will come back to this reaction and this equation shortly. It says see below, it's actually page 17. We're going to be looking at that as one of the reactions of carbon dioxide, because the reason it turns milky is because the carbon dioxide actually reacts with the lime water solution. But if you were asked, how do you test a gas to see if it's carbon dioxide, you bubble the gas through lime water and the lime water will turn from colourless to milky. And again, go back to that YouTube video that I pointed you towards, that shows you the reaction of carbon dioxide with lime water. So go back and watch that video if you're not sure how this test works. Next thing we're going to look at is the preparation of carbon dioxide, and again you should recognise this apparatus. It's exactly the same apparatus as we used for oxygen and hydrogen. So again, make sure you know the apparatus, make sure you could label each one of these parts. So all that's different here, and in each case for oxygen, hydrogen and carbon dioxide, is the reactants that we use, the chemicals that we use to react together to prepare our gas. And again, this takes us back to one of our reactions from year 11. So we looked at when we were forming hydrogen, we reacted a metal with an acid, and that gives us salt plus hydrogen. In this case, if we want our gas to be carbon dioxide, we react a metal carbonate with acid. So a metal carbonate plus acid, and it might be worth writing this general equation at the top of your page or down at the bottom where you have a bit of room. When you react a metal carbonate, so copper carbonate, calcium carbonate, whatever, with any acid, you get a salt plus water plus carbon dioxide. We looked at that last year, and it's also one of your prescribed practicals, so you do need to know it for your practical theory exam as well. So this is the general reaction that we're going to follow when we're preparing carbon dioxide. So you could take any metal carbonate with any acid and it would produce carbon dioxide as one of your products. But again, we want this reaction to be controlled, so we're going to use a dilute acid, and we're going to use dilute hydrochloric acid again, and we're going to use calcium carbonate here, which are sometimes referred to as marble chips. So you do need to know both names for that. If they asked you to write an equation for the reaction of marble chips with hydrochloric acid, you would need to know that marble chips are calcium carbonate. So again, you've got your calcium carbonate sitting here at the bottom of your conical flask. You would add your acid through your thistle funnel, and then if there was a tap here, you would close that off. If not, you would need to put a stopper in the top of your thistle funnel to make sure the gas doesn't escape out the top of the thistle funnel. So this reaction will happen, calcium carbonate reacting with hydrochloric acid. That will happen in your conical flask. The salt that you produce, have a think about what that would be called. We're reacting calcium carbonate with hydrochloric acid. So the name of your salt would be calcium chloride. You would get water, which would obviously stay in your conical flask as well. And you would also get carbon dioxide. And that would pass through your delivery tube into the beehive shelf and then up into the gas jar. Again, there would be a hole here for it to pass into the gas jar. And we just looked at how carbon dioxide is slightly soluble in water. So some of the carbon dioxide will dissolve in the water, which is not what we want, but it's only sparingly soluble. It has a low solubility in water. So most of it will just displace the water rather than reacting with it. So again, when we're talking about the method of collection, we're talking about over water. It's collected over water. This is literally exactly the same as oxygen and hydrogen. So don't think of this as a big thing to learn for each gas. You essentially learn the apparatus and the collection for all of them. And the only thing that changes is the reactants. Okay, so that's how we prepare carbon dioxide. And let's just write a specific balance symbol equation for this reaction. So we're reacting calcium carbonate, which in an exam could be referred to as marble chips. We're reacting that with hydrochloric acid, which has a formula of HCl. And we're forming calcium chloride plus water plus carbon dioxide. And notice how that fits with the general equation that we wrote at the top of the page. So again, pause the video, see if you can write the balance symbol equation of that yourself. And then play the video to check that yours is correct. Carbonate, for calcium carbonate you'll find in the back of your periodic table. So give that a go yourself, because you need to be able to write these type of equations and then play the video to see if you're correct. So having a look at this equation, calcium carbonate, first of all, if you weren't sure how to do that, I'll take you through that now. So calcium is Ca, it's in group 2, so it has a valency of 2. Carbonate appears in the back of the periodic table as CO3 2-. So when we're writing our formula for this type of ion, this is what we call a molecular ion, we need to write down all of the formula first of all. So that's your CO3 part. For now we ignore the charge, so we write CO3. So all the symbols and all the numbers that are part of the formula, i.e. the numbers that are down at the bottom rather than up at the top. We then use our charge for the valency. So the charge is 2-, and that means our valency is 2. So again, write down the formula and then use the charge for the valency. And again, just normal rules apply. We try to cancel down the valencies if possible, and you can see that these two valencies are going to cancel out to 1 to 1, and then when we swap and drop we ignore the ones. So the final formula is just going to be simply CaCO3. If you were swapping down a number to the carbonate, you would have to put it in brackets. Hydrochloric acid then, as I said, the formula is HCl, and you need to learn that. You won't get that from the periodic table. Calcium chloride then, we need to do swap and drop. So calcium is Ca, group 2, so it's a valency of 2. Chloride is simply chlorine. It's not diatomic because it's part of a compound now. It's not chlorine anymore, it's a chloride ion. It's in group 7, so it has a valency of 1. So when we swap and drop that, we get CaCl2 plus water, H2O, plus carbon dioxide, CO2. Remember, dioxide means 2 oxygens. So what we need to do now is balance this equation. So I'm going to, I've written my list. I'm going to do this the long way just to remind you of this process, and just because there's quite a lot going on in this equation. So I've written my list of my elements, and now I'm going to count up how many I have on the left hand side and how many I have on the right. So on the left you can see you've got 1 calcium, 1 carbon, 3 oxygens, you have 1 hydrogen and 1 chlorine. On the right hand side then you have 1 calcium, you have 1 carbon. Be careful about your oxygens because you have 1 here but you also have 2 here, so that's 3 oxygens. You have 2 hydrogens and you have 2 chlorines. So look at your lists, they match for calcium, carbon and oxygen, but not for hydrogen and chlorine. We have 2 on the right for hydrogen and chlorine, and we only have 1 on the left of each. And so what we need to do is put a 2 in front of our HCl. That means I then have 2 hydrogens and I also have 2 chlorines, and so then your equation is balanced. So we're now going to look at some of the uses of carbon dioxide. So the first one is that it is used in certain fire extinguishers, because we know that substances don't burn in it, and it's also denser than air. Those are 2 properties. So again, you're linking your properties to your uses here. So things don't burn in carbon dioxide, and it's also denser in air, so it kind of sinks to the bottom, and it covers whatever the burning fuel is, whatever fire you want to put out. And so you're then starving the fire of oxygen, and therefore it will go out. So I've got a picture there of a carbon dioxide fire extinguisher. So you'll be able to see some are have foam in them and things like that. But if you see CO2 or carbon dioxide labelled on your fire extinguisher, and then that contains carbon dioxide. It's also used in fizzy drinks, carbonated drinks, as it has a low solubility in water, and it gives it that acidic taste. So what causes the bubbles in your fizzy drinks is carbon dioxide. And then finally it is used in dry ice as well. So if you have ever watched or been at a concert or watched maybe a TV program where they have that kind of fog effect on the stage, that is made by dry ice. Dry ice is solid carbon dioxide, so carbon dioxide in the solid state. And what carbon dioxide does is that it sublimes. What we mean by sublimation or subliming is where it goes straight from a solid. So you can imagine almost like an ice cube, but of carbon dioxide rather than of water. So solid carbon dioxide, rather than melting and forming a liquid first of all, it just goes straight to a gas. So we'll do that almost like a little cloud. So dry ice or solid carbon dioxide undergoes sublimation, which means it changes directly from a solid to a gas, because you don't want to pump out you don't have dry ice sitting there and then it melting and forming a liquid on the stage for your performer or your singer to slip and fall on. It changes straight to a gas, and that causes the water vapour in the air to condense. And that forms your kind of fog effect. So think about breathing out in a really cold day, you see that, you can see your breath, it's that kind of idea. You're creating a fog effect at the bottom of the stage, and again, because carbon dioxide is more dense, that happens kind of at the bottom of the stage as opposed to rising up and covering the singer as well. So fire extinguishers, fizzy or carbonated drinks, and for dry ice to create that fog effect on stages. So that's the properties, preparations and uses of carbon dioxide, and the very last thing we're going to look at is the reactions of carbon dioxide, and we've got two of those to look at. The first of those is the reaction with water. So we've talked a little bit about this already, how carbon dioxide is slightly soluble in water, and in fact it actually reacts with water, and that's why when you're putting carbon dioxide into your fizzy drinks, some of the carbon dioxide will actually dissolve and react with the water, and it will form carbonic acid, and that's why all fizzy drinks are bad for your teeth. Things like Coke are extra bad because they've got phosphoric acid in them as well. But all carbonated drinks, all fizzy drinks will have a certain degree of carbonic acid in them, so they will all be slightly acidic. So essentially the equation of this is really easy. Carbon dioxide, CO2, reacting with water, H2O, forming carbonic acid. If you think of the likes of hydrochloric acid is HCl, sulfuric acid is H2SO4. All acids contain hydrogen ions, and so we tend to write those at the start of the formula. So you're taking your two hydrogens from here, there's H2, your carbon, and then your oxygen, and you've got a total of 3 oxygens. Your formula of carbonic acid is H2CO3. So essentially just squish the whole formula together of carbon dioxide and of water, but you tend to write the hydrogen first. So CO2 plus H2O giving you H2CO3. So that's a fairly easy balanced symbol equation to write. So just make sure you know the formula of carbonic acid is H2CO3, or you can literally try and remember it as I just squished the formula of carbon dioxide and water together. And this is partly what causes acid rain. We've talked about this a couple of times in this earlier on in this topic. That carbon dioxide, because it's an acidic gas, when it reacts with or dissolves in rainwater, it forms this solution of carbonic acid, which has a pH of around 5. So that's a weak acid, but you can see that it's quite acidic. It's going towards your stronger acids there, so that can cause acid rain. Obviously you've got sulfur dioxide as well contributing to acid rain as well, and again just below that it mentions your fizzy drinks, but again some of the carbon dioxide reacting with the water forming your carbonic acid. And the very final reaction of carbon dioxide is with calcium hydroxide solution, which is another name for lime water. It's the chemical name for lime water. So calcium hydroxide solution is just lime water. So essentially this reaction is what actually happens in the lime water test. It seems a little bit complicated, but we'll try to make it as simple as we can. But you do need to know these equations, and they're quite commonly asked, because we know that when carbon dioxide is bubbled through lime water, it reacts with the lime water and it produces this cloudy or milky solution. So lime water changes from colourless to milky. But what we're going to look at here is why that happens. What is the chemistry behind it? And it is quite a common question, so you do need to know it. So let's look at the equation for this reaction and see if we can explain what's going on. So remember that calcium hydroxide solution is the chemical name for lime water, and you do need to know that. And I've just spotted that calcium is spelt wrong there. It should be IUM rather than UIM. So you can change that if you wish. So carbon dioxide we know is CO2. And carbon dioxide is a gas. We're going to do the state symbols here as well because it helps explain what is going on. Calcium hydroxide. Let's do the swap and drop up here for that. So calcium is Ca with a valency of 2 because it's in group 2. Check your periodic table for that. Hydroxide appears on the back of your periodic table as OH minus. So what we want to do is put our OH and we're going to put that in brackets. We don't put the little minus sign in. What we use the minus sign for is the valency. So OH minus means that it has a valency of 1. When we swap and drop that, we get Ca, we ignore the 1, brackets OH, and then our little 2 goes outside that. If you need to watch that again, go back and do that to make sure you know how to do that, okay? So calcium hydroxide solution is Ca brackets OH2, and its state symbol, because it's a solution, we give the state symbol AQ, aqueous, and that's from your studies last year of state symbols. And we know that because it's a colourless solution as well, which means that the calcium hydroxide is fully dissolved in solution. And that's why lime water to start with is clear and colourless, because it's a solution, it's aqueous. So it's brackets AQ for that one. Calcium carbonate then, we looked at this earlier, but calcium carbonate, calcium is Ca with a valency of 2. Carbonate is CO3. We can put that in brackets if you wish. And it also has a valency of 2. Look at the back of the periodic table for that. Carbonate is CO3 with a charge of 2 minus. What you can see is these two valencies will cancel out, and so you would end up with Ca bracket CO3. But because we don't have a number outside the bracket, we can just ignore those. So basically, if your valencies cancel out, you don't need brackets. So that's just CaCO3. Now, calcium carbonate is not soluble in water. So what will happen in this case is that the calcium carbonate will come out as what we call a precipitate. A precipitate just means a solid that is formed in a solution. And it's basically because calcium carbonate is not soluble where calcium carbonate is. So I'm actually going to give it the state symbol S. And calcium carbonate, that's your marble chips. It's just a white powder or a white solid. And therefore, if it's insoluble, you've got this white solid that is forming within your solution. And so therefore, that's actually what causes it to have this milky appearance, because you've got white solid particles that are forming within your colourless solution. So that's what makes it go cloudy. Plus your water is H2O with the state symbol of liquid. So that actually explains why lime water changes from colourless to milky, because your lime water, your calcium hydroxide solution, is colourless, and your calcium carbonate that you form is a white solid. So if you've got a white solid forming in a colourless solution, it's going to appear cloudy or milky. And that's just explained in these 2 points below. So that explains why your lime water test is bubbling carbon dioxide through lime water solution, which is calcium hydroxide solution, and it changes from colourless to milky because the calcium hydroxide, the lime water, is colourless, and the white solid, the calcium carbonate, is causing your solution to become milky. So that's the chemistry behind it, but that's not actually the full story. So that's the point at which we've stopped up to now. But actually, if you continued to bubble carbon dioxide through lime water, and it's turned from colourless to milky, if you keep going, if you continue bubbling more carbon dioxide through it, then this reaction happens. A second reaction happens, which actually causes the milkiness to disappear, and it goes back to colourless. So let's have a look at this equation and see if we can understand what's going on. Again, we're going to use state symbols to help us understand. So what happens if we continue to bubble carbon dioxide is that excess carbon dioxide, so this is your excess carbon dioxide, reacts with the calcium, and that's a gas, sorry, reacts with the calcium carbonate that we formed in the first equation. And we gave it the formula CaCO3, and it's a solid. And it reacts with the water that was made in the first equation, and that has the state symbol L. So we could put a bracket around that, and we could say these are products of the initial reaction. And you can see that in the equation above. When they all react together, so excess carbon dioxide with the calcium carbonate and water that was formed in the initial reaction, they form a solution of calcium hydrogen carbonate, and it is soluble. So what that will mean is that we'll go back to colourless. Calcium hydrogen carbonate, again, you could look at the back of your periodic table for this. So calcium is Ca with a valency of 2, and hydrogen carbonate is HCO3 with a charge of minus. We're going to put our HCO3, look at that in the back of your periodic table. Hydrogen carbonate is HCO3 with a charge of minus, so that gives it a valency of 1. So hydrogen carbonate is just all one thing. It's an ion of HCO3 minus. We can't cancel down those valencies, so we swap and drop. We ignore the 1, and we get HCO3 in our brackets, and then a 2 on the outside of the brackets. So we'll write that in our equation. And because it's soluble, what state symbol do you think it will have? So it does dissolve in the solution. So it forms a solution, and that means the state symbol is now AQ. So that means our calcium carbonate is what was making it milky, because it's an insoluble white solid. Whereas now calcium hydrogen carbonate that we formed with excess carbon dioxide is soluble. So it goes back to being a colourless solution. It's a bit like dissolving any salt, any white solid in a solution or in water. It's going to give you a colourless solution. So it's the same as saying, you know, sodium chloride, your table salt is white solid, but when it dissolves in water it forms a colourless solution. So again, calcium hydrogen carbonate, and all these calciums are spelt wrong. I have no idea why, but you can change that if you wish. So the soluble ones are going to dissolve in water to give a colourless solution. So this equation explains why when we continue to bubble carbon dioxide through the lime water, the milky colour disappears, the milky white precipitate disappears, because actually you're forming a new product. You're forming calcium hydrogen carbonate, which is soluble, so therefore it forms a colourless solution. So let's have a think about the journey of your lime water here. So lime water is calcium hydroxide solution, Ca brackets OH, close your brackets 2. It is soluble. So that means that it is a colourless solution. Now this is not given the full equation, but I just want to give you a summary of this. So if we react that with carbon dioxide, what's the calcium product that we form? Well, if you go to your first equation, So the reaction we're going to look at here is the reaction of carbon dioxide with calcium hydroxide solution. Calcium hydroxide solution is better known as lime water. So essentially the first part of this reaction is just your test for carbon dioxide, which is bubble the gas through lime water. And the lime water should turn from colourless to milky. Now here's my lime water in here. You can see that it's already a little bit cloudy, and that's just because as soon as you open a bottle of lime water, you've got carbon dioxide in the atmosphere, which is going to react with it and turn it slightly cloudy, but hopefully we should see it'll become more cloudy. So imagine this is completely colourless, as if it looked like water. There's our lime water in here. What we're going to do in here is I've currently got some hydrochloric acid in here, and I'm going to add some marble chips. Marble chips are calcium carbonate, which when they react with an acid they will form carbon dioxide gas. And that's your way of preparing carbon dioxide if you turn back a few pages. So in here we're doing the reaction between hydrochloric acid and calcium carbonate, which is going to generate carbon dioxide gas, which will pass through our delivery tube, and we're going to bubble it through lime water. So the first stage of this experiment, I'm going to put my marble chips in, and then I'm going to stopper this boiling tube so that the gas doesn't escape. So you can see now that it's bubbling across to the lime water. We may need to add a bit more. So you can see the gas is now passing through into the lime water, and it's turning slightly cloudier. Hopefully you can see that it's turning more milky, more white. So the reaction of carbon dioxide with lime water, essentially what we're seeing in here, is that it turns lime water from colourless to milky. You can say cloudy. Milky is slightly preferred, but cloudy is absolutely fine as well. Okay, and that's because when you react carbon dioxide with calcium hydroxide solution, lime water, it's forming insoluble calcium carbonate, essentially what we added to our acid in the first place. And because it's insoluble, it's appearing as this white precipitate, this white solid within our solution. It doesn't dissolve, and so therefore it appears as a cloudy solution, because you've got little particles of white solid there that are not dissolving, and so we're making your solution cloudy. But if we allow this reaction to continue, if we form more carbon dioxide gas, actually what will happen is we'll form a solution of calcium hydrogen carbonate or calcium bicarbonate, and that actually is soluble, and the solution should eventually go back to colourless. So we've seen that it's gone from colourless to milky as calcium hydroxide solution has reacted with carbon dioxide. But if we continue to bubble carbon dioxide through it, that's in other words an excess of carbon dioxide, then it will turn back from milky to colourless. This is a really common question because it is a little bit strange that it goes from colourless to milky and then returns to colourless again. And that's simply because with excess carbon dioxide, you're forming a solution of calcium hydrogen carbonate, which is soluble and therefore turns colourless again. So we'll have to keep this going a wee bit longer to try and get that excess. You can see it's bubbling away, but not forming loads of carbon dioxide. But we'll keep it going, we'll maybe add a wee bit more acid. We'll get there eventually. Okay, now you can see your excess of carbon dioxide, and our solution has gone back to colourless. Okay, So lime water reacting with carbon dioxide turns from colourless to milky, but on an excess of carbon dioxide it will turn back from milky to colourless, and that's because you're forming a soluble solution of calcium hydrogen carbonate. If it's soluble, it dissolves in the solution to form a colourless solution, which we can see here.